KCC105. We are talking about exponential growth today for week 2's assignment. However, last week, week number 1, we talked about linear growth. For instance, working every hour, earn $12. That's what my money's going to look like. Okay, we're familiar with that concept, and we're familiar with some of the properties. Each hour, every hour, we understand those things. The constant amount. My money changes the constant amount. The graph forms a straight line. These are all things that from week number 1 we saw those. We should be familiar with them. The constant amount is important, but in exponential growth, we're going to get rid of that constant amount. Instead, we're going to talk about a constant percentage. And let's see this in action. Let's see this in real life. When do things grow at a constant percentage? Well, if I log onto this website, bankrate.com, it'll show me all sorts of financial information, which relevant to this class, of course. In particular, if I'm looking at savings accounts, you'll notice that they all have a given percentage. That's exponential growth. If I put my money in that bank, they say, yeah, we'll give you 1.4% average, an average of 1.4% interest. That's going to be an exponential growth. So let's see how that would look in a graph. If I put $500 in the bank, and let's say here I'm talking about 6 years, and I graphed it, that's what my money would look like. And I could show you the formulas on a spreadsheet and so forth, but I'm just going straightforward here. But look at that graph. That still looks like a straight line. So if I'm talking about exponential growth, yeah, there's a constant percentage like those savings accounts. Those are exponential growth, but you need to understand it looks linear at first. It can appear linear at first. All right, so if I wait 6 years, my money looks like it grows in a linear fashion. However, look at this graph now. It goes all the way on the horizontal axis. It goes all the way to 80. I'm going to look at what happens if I leave my money in the bank for, say, 80 years. There we go. All right, if you're looking at that, there's a lot of bars there. It's sort of a visual overload, but you can see you can see a slight curve. And to make it more pronounced, I draw a straight line in there. And yeah, you can see that right here, my money's accelerating. I'm getting more money here. It takes a long time. It takes almost 70 years to start to see that acceleration in the growth. But exponential growth appears linear at first. Look at down here. It looks linear. But then 70 years into the game, I start to see that the effects of the exponential growth. So that's another thing. Growth accelerates over time. How much time? Well, it depends. In that case, it was darn near 70 years. It can be different in different circumstances. Growth accelerates over time. The next thing to understand is, look at this. Going back to the beginning, I started with $500. That's critical. If we're talking about hourly wages, the very first example, you start at 0. You don't work, you don't get money. For exponential growth, you need to have a starting point because you can't take a 1% of 0. You need to have a starting point. Sometimes we call it an intercept. That's a mathematical term, but think of it as a starting point. If you have exponential growth, you need to have a starting amount of money. And we can put it all together. There's a lot of information on the screen right now. I understand that, but mathematically, let's tie it together with a formula right there. I'm going to hit it with you. Y equals B times, parentheses, 1 plus percent times X. Okay, what do all those things mean? B is that starting point we were talking about. How much money do I put into the bank? The percent is the constant percentage, and the X and the Y stand for my time and my money. And of course, both of those change over time. Let's see this in action. So I have here, B is $500. That's how much I start with. You have to have a starting point, otherwise you can't take 1% of 0. My percent, well, that's given. We saw that on the website, the bank rate. That's my percentage of money. And I'm going to convert that to a decimal. I hope that that little trick there, how do I go from percent to a decimal, I hope that makes sense. And if it doesn't, please let me know or reach out. I have some resources I can spell that out. There's the formula that I gave you on the last screen, but now we're just plugging the numbers. 500 goes in the front for the B, and that decimal goes in for the percent. I've got a formula. Now, if you tell me any X number, I can tell you how much money I have. Any X would stand for time. So if I said, wait, put that money in the bank for 100 years, I'll have, well, take that 100 years, take that X, and put it right in there. That's a calculator problem. So I take out my calculator and type all the things in, make sure you do the parentheses first, and then the exponents, and then the multiply. So the order operations, as it were. Once again, there's some details in there. If you're like, wait, you're losing me, I can walk over that in more detail. But for the video, I'm just saying that's the formula. There's my answer. But wait a minute, we're talking about money. We got to dress that up a little bit. So notice that I chop it off 2 decimal places because we're talking about money. And then there we go. In 100 years, I will now have $2,008 and a penny. A lot of information here. But what do you need to know? Constant percentage. You need to know that it can appear linear. We need to know we have accelerated growth. We need to have an intercept and the formula down here. Lots of information, but guess what? There's a comprehension check in Blackboard. Go ahead and take that, test what you know. You can take it up to 3 times, and you can watch the video over and over, and of course you can reach out to me. So the basics on exponential growth, we'll be seeing more of that in the coming weeks.